Hello class, in this video we'll be learning about what is the electrochemical series and how we can calculate the overall cell potential. To begin, I'm going to first introduce you to the idea of the standard reduction potential. The standard reduction potential, or the cell potential for short, is represented by E0, and this is a value which tells us how readily a half cell will undergo reduction. The unit for the cell potential is measured in volts. If we know the cell potentials of multiple half cells, the half cell which has the larger positive value will most likely act as an oxidant and therefore undergo reduction. Let's look at an example down below so I can demonstrate what I mean by this. I've got two half equations, as you can see. There are two things about these half equations which is different to the half equations that you've encountered so far. Firstly, this equation also specifies the cell potential values, which can either be a positive or a negative value. Secondly, the half equation also uses equilibrium arrows, which we will learn about in more detail in another topic, but for now, please understand that this arrow means that the reaction can either go in the forwards or backwards direction. If we know the cell potentials of each half equation, I can conclude that the half cell containing silver ions will most likely undergo reduction since its value is more positive compared to iron 2. Hence, I've answered by saying Ag+ is the stronger oxidant and will undergo reduction. This knowledge is crucial for you to understand how to use the electrochemical series. The electrochemical series is essentially a chart developed by scientists that arranges elements in order of their cell potential from largest to smallest. In other words, it shows the reduction half equations in order of increasing reactivity. As you can see, all of the positive values are found at the top of the list, which means there is a strong tendency for the reduction reaction to occur instead of the reverse oxidation reaction. Whereas all the negative values are found towards the bottom of the list, which means there's a weak tendency for the reduction reaction to proceed and a greater tendency for the reverse oxidation reaction to occur. The cell potential values for each of these half cells are measured and are relative to the standard hydrogen half cell, which has a value of 0 volts. If a species accepts electrons more readily compared to the hydrogen ion, this means it's more likely to undergo reduction, hence its E value is positive, as you can see by this example. In contrast, a species is less likely to accept electrons than hydrogen if its E value is negative, which means it ain't likely to be reduced. The E values recorded for each of the reduction half equations were measured at standard laboratory conditions, which means it was conducted at 1 atmospheric pressure, 1 molar concentration of solution, and at a temperature of 25 degrees Celsius. Please bear in mind that measurements outside of these standard conditions will affect A, the order in reactivity in the electrochemical series, and B, the magnitude of the voltage measured. The electrochemical series is a tool that can be found in the chemistry data booklet, and we could use this information to determine the relative strength of the oxidizing and reducing agent. Since we know that reduction is more likely to take place at the top of the list, this suggests that strong oxidants are found at the top of the list and decreases going down the list. In contrast, the stronger reductants are found at the bottom right of the list, as it's more likely for the reverse oxidation reaction to take place. We could also use this information to predict whether a spontaneous redox reaction will occur between two given half equations and thus write the overall equation for the reaction. And lastly, we can calculate the potential difference of the galvanic cell. Let's go through some examples of how to use the electrochemical series. In a galvanic cell, a spontaneous redox reaction occurs when the strongest oxidizing agent reacts with the strongest reducing agent. In the first example, it wants us to choose the strongest reducing agent out of the list. Reductants undergo oxidation, and the strongest reductant, as shown on the electrochemical series, are found on the bottom right side. Out of these 4 options, we can see that zinc is the strongest reducing agent. In the second example, it wants us to identify the strongest oxidizing agent. The strongest oxidizing agent is found on the top left side of the electrochemical series. As a result, we can see dichromate is the strongest oxidant out of these 3 options. I would now like you to practice at using the electrochemical series. Please pause the video and have a go with this question. In this question, the redox pairs are expressed in a notation where the oxidant is written first, followed by the reductant. Part A wants us to find out what is the strongest oxidizing agent. The strongest oxidizing agent has the greater tendency to undergo reduction, thus it must have the highest positive value, which corresponds to the permanganate ion in this example. Conversely, the strongest reducing agent has the lowest value, which corresponds to the aluminium half equation. In this example, since oxidation is going to take place, we need to therefore choose the aluminium metal as it loses electrons to become the aluminium 3+ ion. The weakest oxidizing agent will be the species that has the lowest cell potential. In this case, it's also going to correspond to the aluminium half equation, and because it's an oxidizing agent which undergoes reduction, therefore we're going to be choosing the aluminium cation. And finally, the weakest reducing agent will be manganese 2+, because the weakest reductants have the highest positive values and undergo the reverse oxidation reaction. In the second half of this video, I want to discuss how do we calculate the overall cell potential in the galvanic cell. The overall cell potential is measured by finding the difference between the potentials recorded at the cathode and at the anode. Alternatively, you can think of it as the potential difference between the site of reduction or the site of oxidation, but the easiest way to remember this would be subtracting the larger value with the smaller value. Let's look at an example. In this reaction, we know that the half cell containing hydrogen will undergo reduction because the hydrogen plus ions is a stronger oxidant than zinc. Hence, zinc metal will undergo oxidation, and this is also shown on the diagram. To calculate the overall cell potential, we subtract the potential of the reduction half equation with the potential of the oxidation half equation. So we subtract 0 with negative 0.76. Keep in mind that two negatives make a positive, so therefore our answer is going to be equal to positive 0.76 volts. I'd like you to now have a go. Please pause this video and find out what is the overall cell potential across these two half cells. In this question, copper 2 is the stronger oxidant and will therefore undergo reduction at the cathode. Therefore, to calculate the overall cell potential, we do this by going the larger value, subtracting it with the smallest value, and this will therefore give us an answer of positive 0.34 volts. Let's now look at another example. In the last example of this video, we're going to use the electrochemical series to predict the overall cell reaction, identify the anode and cathode, determine the direction of the electron flow, and finally calculate the potential difference in the galvanic cell. So what I'll do first is I'm going to refer to the electrochemical series to find out what are the cell potentials of each half equation. Based on the two half equations, I can easily identify that the silver plus ions is going to be the stronger oxidant as it has the larger E value and will therefore undergo reduction at the cathode. As a result, I have illustrated this on the diagram as you can see over here. Now that we have established where the anode and cathode is, I know that in terms of the direction of electron flow, it always goes from the anode to the cathode. So in this example, it's going to flow from left to right. To calculate the overall cell potential, what I do is I'm going to get the largest value, subtract it with the smallest value, and in doing so, this will give me an answer of positive 1.22 volts. And finally, for me to find out what is the overall cell reaction, I need to make sure that my two half equations have the same number of electrons. So I'm going to therefore multiply the second equation by 2. In doing so, I can now add up my two half equations to give me my overall redox reaction. By now, you should be able to meet all of the success criteria in this video. This is the end of the video. Thank you for watching, and I'll see you guys again in the next one. Bye.